All right. Hello, everyone, and thank you for being around, for coming around, for showing up. Today, we are going to look at common study designs in epidemiology. There are so many study designs in epidemiology. It's not possible to cover all of them in 1 hour. We will just try our best to talk about the most common ones that we find around and just kind of talk about the specificities of each of these common study designs and the resources that permitted me to put up this presentation are mainly my notes when I was at the University of Bristol, a random internet search, and obviously my own opinion, my experience with MD thesis. So the reason why I was really excited during my master's wasn't only because at the University of Bristol we have great teachers. We have some people who've literally created their own branches in epidemiology. That's not the only reason. I think one of the main reasons why I was really interested in the master's and I was just writing down everything I was saying, I was trying to keep everything from them. I was trying to meet all these teachers and exchange with them was because I had some experience before going into the master's. After my MD degree at the University of Yaoundé, 1 year in Yaoundé, I learned a lot. I did my thesis with Professor Ashutanta, and she introduced me to, she kind of actually literally held my hand and told me, I can see you like statistics. So take this course offered by Stanford. So they probably have a tuition fee waiver. I think it was, I don't know the cost, but she helped me to apply for the course. And that was my first formal exposure with statistics and health research. But I still had lots of questions after that. So I was analyzing data for MD thesis, students that were preparing their MD thesis. And when I was analyzing, I was still having so many questions. So you can imagine the amount of questions I had when I went to the University of Bristol. So if you ask anyone who was there in 2021, they'll probably tell you that Dr. Kamgan Willie Stephen was all over the place all the time. So that's it. So I thought that after having like got all this experience, all these answers to the questions I had, I needed to create this basic health research series to help people who make the same mistakes that I used to make, concerning the way they deal with confounding, concerning the way they, they analyze their data, or they collect their data, or the way they choose their study designs, what they write in the method section of their protocols and their final report. Yeah, so I did this for you. So thank you for being here, because even if there is just one person who would attend these sessions, you are going to justify all the efforts we are putting in so that the content is always going to be of a certain level. So recap, last week, what did we kind of cover? So last week we covered like the key aspects of systematic error, which can also be called bias. And we saw that if you want to study systematic error by going online and typing different names and looking at what is being said, it would really be hard. I mean, there are so many different types of bias out there, and some of them have many names. So you can have misclassification bias, which could also be called information bias in some sense, which in some sense is still measurement error bias. I mean, one type of systematic error can have so many names. And if you want to study them one after the other, you would spend years and years, and you have the impression that you still are missing out something in them. So you can group all the different types of bias into 3. That's what we saw last week: confounding, information bias, and selection bias. And we looked at this structural approach to like treatment of virtually all types of bias, which is grounded on the theory of Quasar graphs. So Quasar graphs are just like diagrams. It's kind of a language that carries so much information concerning the subject matter, which is epidemiology, biology, and whatever type of sciences you're doing, because this is relevant for all types of sciences. So we use it a lot in epidemiology because there has been a period when there was no formal method to treat confounders. Like, they were very funny definitions. By then, those definitions were not funny. Now we see them as funny. Yeah, that's what progress is all about. And and the new way of treating confounding has to do with the use of causal graphs. So I said causal graph is a language which embeds information on the subject matter and statistics. And causal graphs work with the rules of deseparation. So you can check that. The video is on YouTube. Basically, there are 4 rules, and they are very simple rules. Hopefully, we will have more practical sessions. But I think that before we dive into practical sessions, it's good for us to have this theoretical discussion on the different things, the elements that are going to kind of lay the foundations of whatever practical sessions we have in the future. So yeah, those are the 4 rules of deseparation. And yeah, you can go back to the video of last week to look at them. So what is the plan of the session of today? We are going to talk about main objectives of epidemiological studies. It's very important to talk about the objective, because whatever thing we are doing in epidemiology is to attain your objective. So it's to attain an objective, is to answer a question. So we always need to bear that in mind whenever we are studying something, whenever we are writing a protocol. So after looking at the main objectives of epidemiological studies, we're going to look at retrospective versus prospective. I wouldn't say even retrospective studies versus prospective studies. I'll just say the difference between these terms, and you're going to understand why I'm dissociating that from like the general overview of common study designs. And then we're going to look at ecological studies, or the ecological approach towards studies. And then we are going to have an overview of common study designs, some of which I am sure that you already know, like cross-sectional, case control, etc. And then we are going to talk briefly about Mendelian randomization studies. Where I come from, it's kind of a tradition. And I'm saying where I come from, it's like where I learned epidemiology. Sorry, I come from Cameroon. I was born and raised in Yaoundé. The only thing I know in my life is Yaoundé. Yeah, Mobile, Mana, etc. So yeah, let's go ahead. So main objectives of epidemiological studies. The first one that I'll put here is prediction. So what's prediction all about? So there are just 3 of them. There are just 3 types of objectives. You see this whole public health research everyone is on the internet talking about. It's just for 3 things. It will rarely go beyond these 3 things, or will rarely invent something that's not in these 3 things. If you look at the definition of epidemiology, it's very long, but basically it is the study of determinants and health-related issues, and basically the use of that knowledge to improve health. And you realize that statistics is a core tool of epidemiologists, and they always use statistics to answer their questions that hover around these 3 objectives we are going to talk about. So prediction, what's it all about? So when you are doing prediction, you are interested in doing one of 2 things. Either you're doing prediction to diagnose a condition, or you're doing prediction to do what they call prognosis. That is to kind of tell us the probability that another event is going to occur in the future, given that you already have something happening now. So a very basic, simple example of prognosis is like your life, when you're already diagnosed of a cancer, how much more time, or what's your probability that you're going to survive after 5 years? So that's what prognosis is all about. Diagnosis has to do with trying to say with some amount of precision what is the condition of an individual. So in clinical medicine, if I use a rapid test to diagnose tuberculosis, I am doing diagnostic prediction. So people have come up with, some biomarkers or something that they have put in a chip that can allow a clinician to take a decision based on whether the chip has detected or not the presence of that biomarker or the presence of a certain condition in a person without that chip being the gold standard. So maybe if you want to diagnose tuberculosis, you have to, if you go to any of these places that are accredited to diagnose tuberculosis, they'll always ask you to do a sputum test if you are highly suspicious of tuberculosis, and you have to take a certain bowl, some little sort of container, and you have to spit in it maybe at 5 a.m. or something like that, and go back to the laboratory. They have to analyze, if they do PCR or do further tests, and come and tell you that you have the disease that is the gold standard. But it takes a lot of time, and it's not always needed to have that amount of certitude, the gold standard, before taking a decision. So you use a cheaper test that is more accessible, more affordable, and you use it, and it's thanks to diagnostic studies in epidemiology that you can use TDA, all these rapid tests, all these small chips. So diagnosis has to do with that. You want to know the state of someone, but you don't want to spend all the money in the world. So you just want a quick indicator. We saw that with COVID-19. So we have these key terms, and I can tell you that this is where I have a lot of problems with certain protocols I see around, or certain reports. And I'm really only talking about MD-thesis. We know we have great researchers around, but sometimes in MD-thesis, I don't understand what's happening. And I think we have a good, we have the potential, theses have a great potential to improve public health. But MD-thesis, I want to be precise with that, because there are thousands of MD-thesis every year. So if we can just adjust certain things in the way these theses are done, we can gain a lot, can really improve things. Yeah. So there are this misuse of certain terms. Somebody can start the study and say, I'm looking for associated factors. And at the end, the person is talking about protective factors and risk factors. But you told us that you were only interested in associated factors. So if you're interested in putting up a model, a prediction model, which is not a hard thing to do. So to put up a model is not hard. Now, to put up an accurate model, that is what is hard. Anybody can come up with a model, but it needs to be good. And when you test it in independent data sets, it needs to still have the same type of diagnostic or prognostic performances or performance. But now, if you're saying that you're looking for associated factors, other terms that you can use are predictors, covariates, independent variables, explanatory variables, exposures. So your objective could be to determine factors that could help us predict an outcome. And it's very relevant in public health because it allows us to stratify the population and maybe address certain elements of subjects of a population in order to do maybe secondary prevention. So you've realized with your prediction model that people that are this age, people who travel next, who took a plane, who traveled next to someone who has COVID and who coughs, should self-isolate for 14 days. because they are at high risk of also having COVID. So they shouldn't even take the test. So you see that thanks to this small model, because that's how they build all those recommendations you see around with diseases. And they tell you that if you've been in contact with someone in the same house, self-isolate, you don't need to test. Because they have seen that prediction models have allowed people to say, okay, when you have these characteristics, we can take an action to prevent. So it's still relevant. So I'm not saying that if your study is, you're looking for associated factors, your study has less importance than someone who's looking for risk factors. No, it's just good to define your objective well, and then from there, all the rest should align. So it's always good to use one of these terms and stick to the term. So if you use covariates, remain with covariates till the end. So covariates is more of a term you find in studies that are focused in statistics, in epidemiological methods. So if you're doing a methodological paper, you might use terms like covariates, but you can still use anyone. And it's good to stick to one, because you're going to confuse the reader, because he's reading and he's like predictors, and then you're still talking, and then you talk at some point of covariates, and then at some point you're like exposures. He's going to go crazy. The Y variable generally doesn't have so many names. So it could be is the dependent variable, is the response variable, is the outcome variable. So things change for the X, and we see how the corresponding value for Y changes, and it helps us to say something about their relationship. So here we are purely talking about associations. Now, your objective could be to establish a causal, a cause and effect relationship, or to establish causality. Whether you're doing an experimental study or an observational study, it's legitimate. It's fine if you want to find risk factors with, say, a cross-sectional study. We all know that cross-sectional studies are not the best for causality. But if that's all what you can do, it's good for you to tell us from the beginning that you're looking for protective factors. And then in your discussion, you're going to take into consideration the limitations of cross-sectional studies. You're going to take into consideration certain ways in which the study was conducted to discuss your answer. But now you have clearly declared that I am interested in causality. Most people know that observational studies are not the best. So it's Professor Jonathan Stern who likes talking about that, because informal causal inference. That's most people want to determine protective factors and risk factors. They do a case control study when they say, and then the title reads associated factors. And then when they are developing their protocol, they talk about associations. But then when they come to the discussion after doing the results, since they have p-values that are very small and odds ratios, some are way bigger than 1 and some are way smaller than 1, they do the discussion and they talk about protective and risk factors. And it's not proper, because if you keep that, if you feel that you are going to be doing this all the time, your method might not even consider all the different ways of controlling all these confounders and measurement error and all the other issues that that can bias your conclusions. So it's always good to clearly declare what you're out for, and you stick to that, and you try to give results that are as unbiased as possible, or as you can. So here, the X variable is not going to be called like just predictors, because here, we don't care whether the predictor has a causal relationship. We just want to know whether it helps. So I have to go to work. I don't have a watch. But every morning, the cock makes cocorico, and then the sun rises. Okay, it's clear that the hen or the fowl that made cocorico is not causing any sun to rise. That one is clear. But at least it helps you to know that, hey, it's already cocorico, so I need to wake up. Because generally, when this cock or this fowl makes this sound, the sun rises, so I need to wake up. So I'm taking a decision based on something that's just a predictor That's just an associated factor. It's not causal. It has no causal relation, cause-effect relationship. Okay, so here, another thing I want to say is that we are generally too optimistic. That is, in one study, we want to determine 10 risk factors. This is not possible. Even people that have thousands of data sets of subjects in a study, they try to deal with one risk factor at a time, from the beginning to the end of the study. They have their one statistical test that they do for code analysis, and then later on they do an adjusted analysis, taking into consideration confounders, to have an XY association which is free from confounding. Just one X. So, scientists, we like to, in science, or scientists like to take a big problem and cut it into small manageable bits, so that at least they can deal with a small bit in a thorough way. And then another person will take another small bit, and that's how we can build the whole picture of whatever thing is happening. So we are sometimes too optimistic. Somebody has 300, 400 participants, where he's trying to get like 5, 6, 7, 10 risk factors. And then at the end, he puts all the factors in the multiple regression model, and he says that these factors are independently causal. It's not proper, and sometimes it can be dangerous. So these are the terms we can use when we are out for causality. And these are the terms we can use for Y variable. So the reason why I put a cause and effect, a parent and a child, is just trying to refer back to the terms that are used in causal graphs. So this is a simple causal graph, where X, the parent, causes Y, the child. And if whether you're doing an observational or a randomized control trial, your objective is to estimate the strength of this line, the strength of the association between both of them. If it's a randomized control trial, the strength of association is going to be the causal effect, because randomized control trials are really the best when it comes to establishing cause and effect. Well, there is a better one, which is systematic reviews of randomized control trials. We're going to see that in a few slides later. So that's it for causality. Another objective, which is very common, and very important, very, very important, because you cannot do public health if you cannot estimate quantities. So estimating quantities is very important. So you might want to estimate a proportion, that is a prevalence and incidence, which is not an effect size, because when you have an association, an odds ratio, a risk ratio, all these things are what they call effect sizes. That is the size of the effect of X on Y. But you might not want to do that. Your objective might just be to estimate like quantities, proportions, or estimate rates. So there's a difference between rates and proportions. Hopefully, when we will talk about survival analysis in one of these later sessions, you will understand the difference between rates and proportion. So we can also estimate quantities, as I put there in bracket, like what is the mean blood pressure of this population? It requires a whole study design on its own. So if someone is doing a study design to determine causality and has a mean blood pressure, it doesn't mean that that's the mean blood pressure of that population per se. So it's not always good to just take like summaries of like things that other studies have found when that wasn't their objective. That was not even their objective. And then you just use it as an answer to a question you've been asking yourself. So if you want to know what's the proportion of people living in Limbe, and you have a randomized control trial in Limbe, and then they have a proportion of I don't know, 38% of women. It doesn't mean that in Limbe there are 38% of women. If you want to know the proportion of women in Limbe, you have to conduct a survey. You have to use a design that will help you to have that correct answer. Well, that was just an aside. So there are other measures of burden of disease that are common in studies that evaluate the economic cost, economic, how they call it, health economics is a very important part of public health. We don't have so many health economics in Cameroon. Health economics, there are types of assessments that they are good at, called health technology assessments. It's very important when you have a health related project and you want to estimate things that are around the technicalities of the project. We don't have many of them around. So if you're interested in doing anything in public health, I suggest you just consider, because you have loads of opportunities. You'll probably be on every project. And yeah, we have DALIs. I think it's days of adjusted life years with, no, disability adjusted life years, something like that. So it's for people with maybe mental health issues that can't work every day, or you have a fracture, and then they have to make some adjustments for the fact that due to your disability, your life years could be considered differently with someone who's been healthy all the time. And it's kind of the same on the underlying concept for the YDL. What else? So you could have as objective in your epidemiological study to measure a complex exposure level. So just imagine you want to measure air pollution in Yaoundé. So Yaoundé is quite big. Yaoundé has many neighborhoods, and you need to have one value that will estimate the level of air pollution in Yaoundé. Maybe you want to kind of report this value to the Cameroon government. So you would need a specific design. Maybe you even call engineers that will help you to design methods of capturing certain health pollutants. Okay. Now let's talk about the term retrospective and prospective. So retrospective, usually you'd find a study called a retrospective study, but really retrospective and prospective just kind of indicate the way data was obtained. So retrospective studies look back. We look at archives generally, or routine data, routinely collected data. Prospective studies. In prospective studies, the data is collected for the sake of the study. And obviously it's better because the data is more accurate and you can measure things in a more standard way. In retrospective study, you have to manage what you have. So whatever way anything is measured, you just have to do with it like that. But in prospective studies, excuse me, let me just try to mute someone. Okay. But in prospective studies, you can use the gold standards, you can use the best ways of measuring things. It's more expensive, it's more time consuming, but it's more precise. So there are certain things you're not going to be exposed. You're not going to be exposed to certain things that you will be exposed to in retrospective studies, such as measurement error. So there'll still be some amount of measurement error, but it's probably going to be less than if you did a retrospective study. Confounding and all that, because if you have to use already collected data, you might not have all the variables that you need to control for confounding. So you're going to be limited to the variables that are present in a data set to do your study. So you can imagine the type of things that can happen. But retrospective studies are very good when you don't have time and when you need to plan a smaller study in order to do a bigger one. So it really is really informative of the type of obstacles you might find to do the same study in a prospective way. So it's more of a description of how you got your data than, well, a real design per se. I think it's an element of your design. So we have ecological studies. So ecological studies are studies where we are interested in groups of people. So instead of studying one person and including individuals in your data, building your data set with data from individuals, you build your data set with aggregate level data, aggregate data. So it could be a group of people, it could be students in a school or a school, it could be a neighborhood, it could be a quartier, Imana, Etudi, Guso, it could be a whole city, Yaoundé, Douala, Marwa, it could be countries. So when the COVID pandemic was declared in Cameroon, I did something, and I didn't know that they call that an ecological study. What I did was that I was wondering why markets were open here. People were just behaving as if though there was no COVID in Cameroon, and we were not having the type of cases that people have abroad. Sorry, some people could argue that is because, we don't measure, we don't have sophisticated tools for diagnosis and measurement of the condition in Cameroon. That's why we have the impression that there was no COVID. But I think that when there is a critical situation in a population, you can see it, you can feel it, though it's not a very precise way of appreciating things. But if people were at that period, people were dying of COVID, but not like in other countries. So what I did was that I went online. There are free resources online. I just downloaded every country's COVID level and every country's latitude. My null hypothesis was that as you get closer to the tropics, maybe the rate of transmissibility of the disease is reduced. So what I did was that I took every country in the world and I considered their latitude. So the latitude of the center of that country. And I put it in SPSS, and I just try to correlate the latitude with the cases of the COVID cases. I did the Pearson's correlation and Spearman correlation coefficient to see whether there was any trend. And I realized that there was a trend. As your latitude reduced, so as you leave from this 90 and you come to the center, that's 0, that's here, the number of cases reduce. So I tried to explain that. I tried to give myself to check online what could explain this. And yeah, that was an example. That's an example of an ecological study. I didn't know that that's how they called it. And there are some good things about ecological studies and bad things about ecological studies. Not really bad things, but things you should take into consideration when you want to make generalization. Another example of an ecological study was seen in Nadine Study. So if you follow us or if you subscribe to our YouTube channel, you'll see a very small summary of about 4 minutes that I made of a student who worked with me about 2 years ago, Dr. Fuda Nadine. Maybe some of you know her. And she was looking at loss to follow-up at Hôpital Gynéco-Obstétrique. And one interesting thing that she did was that she was stratifying distances away from Hôpital Gynéco to determine whether distance was associated or could be a risk factor of being lost to follow up during pregnancy. So just quickly, when you're pregnant, you have to be followed up in a hospital. But some people start their follow-up in a hospital and then nobody knows where they are going to. And yeah, this is what she did. So she used Google Map, and then she tried to draw circles around. This is what she did. She drew circles. This is Hôpital Gynéco here, this red cross. And then she drew circles of about 5 kilometers away, and and then kind of redistributed Yaoundé into zones away from Hôpital Gynéco. So you have zone A. This is what she had: zone A, zone B, zone C, zone D. And she realized, and you can see that the percentages are seemingly increasing as we leave from here down here. So there are so many things you have to take into consideration before making any conclusion of absolute association here. But well, when you're just looking at this, it looks like something is happening as you're leaving, as you're going away from hôpital gynéco from zone A to zone D. The strength of evidence will probably not be strong because not be high because you have just few people away. So the statistical power of this is going to be affected by the fact that few people were far. But anyways, you have the impression that as we leave, lots to follow-up cases increase. Now, ecological studies, and it's an ecological study, it's an example of an ecological approach towards answering a question because she's not considering everybody's, because what she would have done, what she could have done is that she could have just recorded the exact distance that Google Map gives her. Or she would maybe, yes, she could have calculated for everyone and then just put everyone's exact distance. And instead of doing like a chi-square test, which she did, she could have done like just a simple t-test, but generally the best thing is to just work with regression models. So if your outcome is binary, you probably use a logistic regression model and you're going to have a continuous outcome rather than an ordinal outcome. I mean, a continuous predictor variable rather than an ordinal predictor variable. I'm talking about zones. Here it's ordinal, it's more of categorical. And it would have been just distance in kilometers. So it would have been continuous. People would have had 1.1 kilometer, 1.2 kilometers, and all had 300 or something participants would have had their values, and then we just do the test. It would have been more accurate. But anyway, let's go. This is an approach which is valid though. Just that we're going to look at the lows, the disadvantages of using ecological approach. So ecological studies are not really a type of study design per se, rather an approach which can be adopted in all other designs. So you probably know about clustered randomized trials, randomized control trials. So it's a randomized control trial, but instead of dealing with individuals, you're dealing with groups of people. And sometimes it's the best study design you can use to answer a certain question. So it's still the ecological approach because you're not using individuals, but you're using aggregate level data or aggregate data. Now, beware of selection, information, confounding, and this new type of bias called ecological bias. So what's ecological bias is when your unit of observation is quartier in Yaoundé, that's streets in Yaoundé, or districts in Yaoundé. And then your study talks about districts in Yaoundé. But you come and you're concluding, and the person is concluding on individuals in Yaoundé or individuals in Cameroon. You're studying districts in Yaoundé, and you realize that maybe there is a positive trend between, I'll take a simple example. Brasserie du Cameroon probably has a way of doing the stocks they send to each city. So they know that I'm sending this number of lorries or whatever to Yaoundé with this number of liters. So that's the yearly consumption of Yaoundé, the yearly consumption of alcohol or beer in Yaoundé. They know the same thing about Douala, about Betwa, Konsamba, and other cities even out of Cameroon. And you might want to see whether there is a certain trend between them as we leave from the south to the north of Cameroon. So there is aggregate level data. So you might want to see whether in each city, or you might want to see whether the cases of, let me say, coronary heart disease in each city is correlated with the consumption of alcohol. And at the level of cities, you might have an association, but that association shouldn't be translated onto individuals living in this area. So that's what they call ecological bias, because what you observe when you're considering bulks or chunks of people might not be the same thing that you observe if you're considering individuals. So this is an example of what we could have with the Nadine study. So I won't know because I don't have the data for everyone. But zone A, if you go back to what she had, zone A had 38%, zone B was higher, 43%, zone C was almost the same as zone B, and then zone D was 77%. So zone D is the highest here. Loss to follow-up was 77% is high. Zone B and C were almost the same level, with C a little bit lower. And then zone A was lower. So if you draw a line and consider only the zones and the summary, it will be like this. You have a positive slope. But now just imagine she considered 1 kilometer like group, like people, instead of taking 5 kilometers, she takes 1.25 kilometers, and we have 4 groups in each of these zones. And then you instead realize that people who are further away in the same zone have lower rate of loss to follow up. So in each group, the tendency is the opposite. So it's reversed. It can happen. I don't know whether it was the case, but if this ever happens, it's an example of ecological bias. And one of the things you should just do to prevent it is we should just be careful when we're making conclusions about individuals when we studied groups of people. So even in cluster randomized trial, you can have these type of things. I don't know to what extent it's common, but it's just good to have that in mind. Now, this is the pyramid everyone probably has seen somewhere in medical school or in the internet, like the hierarchy of evidence. And below here, in some diagrams, you have case reports and case series. The truth is that no study design is absolutely better than another. All depends on the objective, the time, the money, and ethical issues, and probably other determinants. So I think this pyramid holds when your objective is the B objective, which is causality. So if you're interested in causality, the study that's going to give you the best level of evidence is definitely going to be systematic reviews of randomized controlled trials. That's for causality only. Maybe if you're doing prevalence, yes, you have systematic reviews of prevalence studies. That's cross-sectional studies. So if you do a systematic review of cross-sectional studies, yeah, you have a better level of evidence. But it would be inappropriate for anyone to use a case control study to determine the prevalence of whatsoever situation. It would be inappropriate to take a cohort study and you want to determine the prevalence. So I'm just saying that this pyramid really holds, like this pyramid in its entirety makes sense when you're talking about causality. So people just emit to, sometimes when we're talking fast, maybe among researchers, we don't need to precise that. But if somebody is not used to and just gets into all these things that are being said, the person might believe that if you're doing a study and it's not a randomized control trial, the study is not a good one. Or if you're carrying out a study and it's not a cohort study, at least to determine causality, because with randomized control trials, ethical reasons you can't do it. So people will be like, no, I want a prospective cohort study. If your study is not prospective cohort, it's a bad study. It's not true. You might want to determine the prevalence of a disease. And the only choice you have for that is a cross-sectional study. Well, sorry. And why are we even sorry? That's what you have to do, so it's fine. So nobody should feel like, nah, my study was just a cross-sectional study. Or my study was just a CAP study. No, there are certain things that CAP will do that others won't do. So no study is absolutely better. And then sometimes you might have to answer, for example, in the COVID period, what I used to hear around was that, I don't know to what extent it's true. I was not really much into it. I was looking at it from a distance, what was happening in the Western world. And people used to say, we don't have time to do randomized control trials. We don't have time to do randomized control trials. So they will have to do other types of study design to use. And at that point, it's appropriate. Okay. Let's dive in. Let's just look briefly at each of these study designs. So surveys or cross-sectional studies are studies where we don't care about whether the participants have an outcome or an exposure. We just go into the population as quickly as possible. We try to get those that are eligible, and then we determine the prevalence of whatever condition is of interest to us. And cross-sectional studies, their vocation is to quantify the burden of disease in terms of prevalence, in terms of means, in terms of averages, things like that. So if you want to have a quantity, a cross-sectional study is analogous to tasting how much of kanwang is in a soup. Do they put kanwang in granule soup? Do they put kanwang? They don't put kanwang in granule soup. Okay, well, let me just say salt. If you want to taste the amount of salt in granule soup, it's really like you have to carry out a cross-sectional study with the soup. Okay, so you will come at the end, at that point, at that time, you will turn the soup, and then you will taste. And you are the minister of public health of your soup, and you are going to decide, we don't have enough salt here, I'll add. So you take a decision based on the measure you have taken of the burden of disease. Well, adding salt is not good. We all know that. So with cross-sectional studies, you can also do very interesting things, is that you can start seeing patterns, you can determine patterns, and it's good. It's good to put patterns to evidence patterns, because they can help someone to to build a prediction model. It can help people to build prediction models. It can help people to develop hypotheses for causality. So cross-sectional studies can allow us to get prevalence, to get the burden of disease, a measure of something. If you want to get the pollution rate, the pollution level in Cameroon, you have to do a cross-sectional study. If you want to know the pollution level now in Cameroon or in Yaoundé, I have to quickly run a cross-sectional study. So normally, maybe in other places, they are constantly measuring pollutants. So they don't need to really carry out the study to determine something in a punctual way. They just have a system that just keeps updating itself. People talk about multiple cross-sectional studies. So the time is going like that, and somebody just takes every month, you have an update. The next study design we're going to look at is case control studies. So case control studies come in to do what? To do one thing that a cross-sectional study can't do. And while it's doing that thing better than a cross-sectional study, it can't allow us to get any prevalence, because you're the one determining the proportion of whatever conditions in the population. So a cross-sectional study is a little bit like, let me put it this way, making your own lemon juice. So you like concentrated lemon, you like concentrated lemon, but when you go and buy lemon, when you go and do sports in Pakovita and you meet these ladies that sell lemon juice, it's very diluted. At least for me, I like lemon. So when I drink it, I feel that it's not enough. That's what happens with the cross-sectional study. You don't determine how things are distributed in your population. You just go and whatever thing you find there, you take it. But in some situations, the condition is rare. And if you want to determine patterns, you will not have enough statistical power. That's what they say. So you not have enough subjects to get considerable associations. If you do that with a cross-sectional study, you might have 100 participants with just 2 people having a condition. You can't really run any statistical analysis or detect patterns. So you do what I do when I realize that my lemon juice outside is not good enough, or is not having enough lemon. I come back home, I buy lemon, and I press myself, and I add just a little bit of water. That's what I like to do. But later on, I drink a lot of water, so don't say that I only drink concentrated things. The nutritionist told me that it was good, what I was doing, so I keep doing it. So you come up with your own concentration of lemon juice. So I buy my lemon in the market and I come to the house, I press it and I concentrate it the way I like. That's exactly what you're doing with the case control study. So in the case control study, you determine the concentration of whatever thing you're studying. As a matter of fact, unlike cross-sectional studies that start when people have the exposure and outcome, case control studies start with people that have the outcome only. And then later on, for each person that has the outcome, we'll try to look for someone who is similar, but not too similar. So generally, if we match for age and sex. We don't match for many more things. Or else people will be too similar and will not have differences to gain some statistical power. So there's something I see which is deplorable. This is really, really a basic error. People want to get prevalent and they adopt a case control study where they determine the control exposure ratio. I mean the case control ratio. So you have said that your ratio is 1:1, meaning that your prevalence is always going to be 50% if you want to calculate prevalence. So it doesn't make any sense. So case control studies are meant to increase statistical power when you want to get patterns and maybe the disease is rare. Because even that's why I'm saying that it really depends on the situation, because in some cases, case control studies will give you better evidence faster than cohort studies. Because if the disease is rare and you have to wait for years for it to develop in the population, and you're doing a cohort study, you wait for so long. There is a whole epidemiology of rare diseases, and there are people who are specialized in that. But I think that at our level, we can already see that case control studies might still have their place to determine causality if the trait is really rare, the characteristics is too rare. Now, if you have time, like 50 years, 60 years, okay, fine. You expose the people, or you watch people who are exposed, You watch people who are exposed and people who are not exposed. And yeah, there are cohort studies that have gone on for so many years. Matter of fact, my dissertation at the University of Bristol was, during my dissertation, I used data from ALSPAC, the Avon longitudinal study of parents and children. That study studies people, their children, and the children of their children. So it's a study that considers transgenerational changes, lifestyle changes, molecular changes, sociological. I mean, it's really an integrative approach towards causality. So yeah, that's what I studied, and the study has been going on for, I think, over 30 years, something like that. So yeah, for certain situations, considering your timeline, this might be the best thing you go for. So longitudinal studies, what are longitudinal studies? So we have cohort studies and longitudinal study. Any study that has the term follow-up in it is a longitudinal study. So you could have cohort studies or randomized control trials. They are all longitudinal studies. So the difference is that in randomized control trials, we have random allocation. In cohort studies, the allocation is not random. That is, the people that find themselves in an exposed and unexposed groups were not randomly assigned to that group. So why is randomization that important? Because both of them are longitudinal studies, but there are so many findings at the cohort study level that has not carried on to randomized control trials. So people do, for example, I cannot clearly remember, but there are lots of papers where people find that taking maybe vitamin E prevents stroke. So when the cohort study realizes or identifies vitamin D like in the diet as a protective factor, what happens is that pharmacological companies are just going to empty themselves on that paper and be like, we are all going to try randomized control trials very fast. I want to be the one who discovers it, and then I launch my new product. You see, so there's a lot of money that goes into studies like this, like cohort studies that find things, and then later on they realize that due to problems that all observational studies have, which is major ones, confounding, the findings in cohort studies don't carry over to randomized control trials. So yeah, basically that's the difference between both of them. It's randomization. So I had to put a diagram here to put dice. So when you have participants that you select, they get into a machine, which is the randomization process, which is like dice throwing, and then we randomly assign people in both groups. So what randomization actually does in terms of directed acyclic graphs is that randomization destroys whatever link confounding has with exposure. So if I have to draw it here, let me try to draw it here. Without this tablet, I'm going to draw it. I don't know what's wrong with this. Anyways, let's go. So generally, we know that we have X, and X is the exposure, and we want to check whether it causes Y. But we have confounders that are common causes of X and Y. Really, really problematic. So these confounders are very present. So they really act in cohort studies because individuals are not randomly assigned to groups. But the confounders now, when you randomize, it kind of breaks this line. It destroys this line because in each of these groups, you have the same proportion of confounders as people in these groups. Because it's just randomness that was defining the way people are distributed. So we don't have issues of confounding. We're not supposed to have confounding issues in good randomized control trials. That is why they always remain the best source of evidence for what they call primary studies. So just small vocabulary, primary studies are studies of this type. All these studies here are called primary studies. So they are primary studies because they are one study. But systematic reviews are not primary studies because they use primary studies to work. Okay. Now, systematic review, okay, let's just look at meta-analysis because I feel that meta-analysis really gives you a good idea of what systematic reviews are all about. So just imagine that we have a study in Spain, I would say in Senegal, a study in Côte d'Ivoire, a study in Cameroon, a study in Gabon, and a study in Burkina Faso. So we are all sub-Saharan African countries. Do program and interventional trials fall under? Oh, please, what do you mean by program? Can you put on your mic and say something and tell us what you mean by program?
Good morning, everyone.
Good morning.
I mean, Vanessa. Yes, I mean, for example, an individual or an organization carries out a program or a project and then wants to evaluate it at the end of the project and see whether it was effective in one, and they do it in two groups of individuals, and then they want to evaluate it at the end, and they want to see whether it was effective in one group and not effective in the other. They are under randomized control trials. That's what I'm asking.
Yes. When that's an experimental study for sure. So if they put people in groups and in one group there is an intervention going on, or there is a particular exposure that's being introduced in one group and the exposure is not introduced in the other group, that's an experimental study for sure. Now, the experimental study could be randomized or not. And it is strongly recommended that randomization be implemented or be part of the rundown of every experimental study in population health sciences. So yes, I don't know whether I would say it's an RCT, because to be an RCT, you need to be randomized. There, I know you said it's controlled, so it's controlled. So you just need to check whether there was any element of random allocation into groups, because they are what they call pseudo-randomized or not randomized trials. They don't have all the benefits. All what we have talked about so far are randomized control trials, because that's where the magic occurs, in the randomization into groups. Okay, great. So yes, so we have Burkina Faso. So all these are sub-Saharan African countries. And just imagine we are trying to get the prevalence of a health condition. And in Senegal, it is 12.3. In Côte d'Ivoire, maybe you don't even want the prevalence. Maybe you want the causal effect. I just put prevalence here, but imagine we want to determine whether I'll just say, taking, give me any substance, any nice substance. Vitamin C. So taking vitamin C prevents, I don't know, chicken pox in children. So when you give vitamin C, just imagine that they want to test whether they do randomized control trials to see whether taking vitamin C, because when I had chicken pox when I was a child, they used to give me Sprite vitamin C. No publicity here. That's what they used to do. I don't know where they got that thing from. I don't know whether it helps. Maybe it helps. I need to read that. So maybe they want to check whether vitamin C can prevent children from having chickenpox, or can prevent the severity of the chickenpox, because having chickenpox when you're a child, I don't think it would really kill. Yeah, everyone has it and it finishes. And it's better to have it when you're a child. That's what I heard. So yeah, and then you have the effect size here. It's maybe, I don't know, let's say 0.75. Odds ratio, here is 0.8. Here is 0.6. Here is, no, Cameroonian things always come out a type. So let's just put 1.1. And then here we have 0.9. And then here maybe we have our friends Burkina Faso, they are always supporting us. So put 1.2. Now, in systematic reviews, you would have to take the average. You'll be taking the average of all this in some way. So this is what they call fixed effect meta-analysis. There is random effect meta-analysis, other forms of meta-analysis, network meta-analysis, component-based network meta-analysis, component network. So there are so many different types, but the basic idea is that you want to have the best form of truth. So you take everybody's perspective and then you put it into one way. So if you are lucky enough to have a population like this population, Senegal, Cote d'Ivoire, Cameroon, Gabon, Burkina Faso, this population is likely to be a homogeneous population, and the study is likely to, if the study was conducted by different groups, but their protocols are similar or their reports are similar, you have what they call little heterogeneity, meaning that the populations, the studies can be combined. If you have little heterogeneity, you can do this type of thing and you're going to have the best possible estimate of whatever situation you're interested in. So that's what meta-analysis is all about. But that's really what systematic review is all about. So if there is no way of doing a meta-analysis and having a numerical average through whatever means, you have to give an average, some sort of average, like a synthesis of the reviews that you did of the articles. Because in some cases, combining things don't make sense. So it requires of the person to now use their knowledge, their experience in the field, and discuss with other experts to combine the results in a way that's not numerical. So that's what they call systematic reviews without meta-analysis. So we have an excellent presentation. It's in French, so I hope you have no problems with following things in French. I only speak in English because my French is not really good. My English is not really the best, but I'm better at English than French. And that's why I'm always going to use English. But if you have questions in French, feel free to ask. I can use French too. So we have a really nice presentation by Dr. Binyarim, who is very experienced in systematic review. He has over 140 systematic reviews published in all the Lancets you can think of. We have Professor Ngufat Tago, who is, I think, one of the most prominent biostatistics professors in Cameroon. So it's really I really recommend that you look at it. It doesn't have so many views. I don't understand why, but just try to look at it. So it was here. We were privileged to host the event. And yeah, the integral workshop is available online freely on our YouTube channel, Fishboard Community. Yes, some common, we're almost through, we're almost done. Some common epidemiological studies, the problem with observational studies and causality. So there are many problems that observational studies can present, especially if you're dealing with retrospective studies. Now, even with prospective studies, we have issues. and particularly issues with confounding. Why? Because we don't know all the confounders. So we know that there are lots of things we don't know. And now the things that we even know, sometimes we don't measure it well. It's very hard to have a perfect measure of confounding. Generally, measurement error in study designs are done to avoid exposure and outcome measurement error. But measurement error should also come in when we are measuring confounders, or else we're going to have what they call residual confounding. So residual confounding comes from the fact that in observational studies, it's not possible to control for all the confounders, and it's not possible to control for all the confounders perfectly. Whether it's at the analysis stage or at the design stage, we almost always leave out some confounding, which caused what we earlier talked about, which is the fact that findings in randomized control trials don't generally carry over to findings in cohort studies and other observational studies often do not carry over to randomized control trials. The problem with randomized control trials is that they are the best source of evidence, but ethical issues, we can't use randomized control trials to study risk factors, and they can be very expensive and time consuming. And sometimes you want an answer right now and want to take a decision. So what do we do? Do we always do a randomized control trial? No. So there is good news. We have what they call instrumental variable studies. In this case, I'm going to talk about one in particular, Mendelian randomization. So we earlier saw that randomization was the magic thing that was happening in RCTs, and that will make RCTs be at the top of the hierarchy of causal inference or studies for causal inference. And the reason being that we have randomization, but in every individual in the world, there is a random process that took place at some point in their lives. That random process is the building up of your genetic constituents. So we know that the human person is made up of, every person has DNA, and DNA has information about proteins that will help you have whatever thing you have right now, like your body, like everything. And a gene is kind of DNA equals 23 pairs of chromosomes. Each chromosome has a section that's responsible for the production of an amino acid called the gene. And there are variations that happen in the genes. And the way those variations are passed on to the next generation is independent of whatever confounder, whatever characteristic of the parent. So this observation was first made by Gregor Mendel, I think it's Gregor Mendel, the monk who was a biologist and who made the laws of genetics. And it's called, I think it's the second law of Mendel, the law of independent assortment, something like that. And this was kind of, one of the pioneers of this was George David Smith, who was one of my, he's still alive, was one of my tutors in the University of Bristol. And I had the chance to get this firsthand from him. It's really interesting when he talks about it. If you're interested in Mendelian randomization, just go online, and on YouTube, you go and type George David Smith. He has given loads of talks on this. And this is the nice bit about Mendelian randomization, is that the randomization that we could only do with randomized control trial, given that it already occurs in each individual, we can use this information, these genetic variants in people, to overcome the problem of confounding in observational studies and have the quality of evidence of randomized control trials without doing randomized control trials. Well, it's not always possible, because for some traits, if you're studying something really rare, if your X is a rare thing, if X is a rare variable, I don't know, I can't think of anyone right now, and we haven't had the chance, or people, studies or researchers in the world have not yet had the chance to determine the portion of the genes that are associated with the rare trait or the trait that's not very popular, it won't be possible for you to do a randomized a Mendelian randomization study. But now, with what they call GWASs, that's genome-wide association studies. There are many GWASs out there, given that now technology has allowed us to kind of sequence genes at a cheaper cost. Sometimes you just have a small diskette like that that has so many portions of the DNA, so many portions of the DNA, and you can easily, they call it SNPs, single nucleotide polymorphism. We'll have the chance to talk about all these molecular epidemiology issues later. So yeah, there is an abundance of GWASs out there, and you can easily go on the internet and just look for the genes that are associated with, let's say, BMI. So if you want to find out if BMI or being maybe obese can cause lung cancer, you don't need to look for people, make them obese, and look for others, make them slim, and then see whether they develop lung cancer. That's not ethical. What you can do is that you just go and check whether there has been genome-wide association studies concerning BMI. And then you take all the genetic variants that are associated with being obese, and you make sure that those genetic variants are also associated in other genome-wide studies with lung cancer. And that we don't have, this is a technical thing, just take it for it. We're going to talk about this later. We're out of time. And yeah, so, and that there is no pleiotropy. That is, there's no horizontal pleiotropy. That is, the only way in which these genes act on lung cancer is by passing through BMI. That's the first thing. The second thing is that the genes should be strongly associated with BMI. That's the second thing. The third thing that we should take into consideration is that the genes you have put, or that your candidate genes for Mendelian randomization studies, should not be linked, should not have any link with confounders of this XY relationship. Generally, we don't have ways of testing all these assumptions, but generally they hold and they give extraordinary results. So this is an example of what Mendelian randomization study could achieve. This is a slide, I just snipped it from YouTube. You can go and read this. You can go and read this video. It's just about 38 minutes. Mendelian randomization, how our genes conduct randomized clinical trials. Okay. So on this first blue box here, we have what a pharmaceutical company did. The pharmaceutical company wanted to test whether selenium complements, you know what they call these food complements that they always give to people. They want to find evidence that selenium actually prevents prostate cancer. So what they did is that they randomly assigned people to groups that would take selenium supplements and groups that would not take selenium supplements. They spent $114 million in this study, and they found that there was no effect. $114 million in CFA francs, you multiply by 1,000 and divide by 2. So it's 114 billion divided by 2. So it's about, I don't know, 57 billion CFA francs, just to find out that it wasn't working. Now, this is a Mendelian randomization study of the same thing. This is the answer that they got here. The relative risk was 1.04. The confidence interval showed that there was high. There's no reason to reject the null hypothesis of independence. And here is almost the same thing. Relative risk of 1.00. And you see the confidence interval is kind of similar. Okay. And how much does the Mendelian randomization study cost. If the genes have already been found, this thing is going to cost you just some time and some clicks on the internet. Because anyone can do a Mendelian randomization study now. There are websites that do that. You don't even need to have a statistical package. Yes, it just takes you a few clicks and you have the same level of evidence. I think at this time, when they did this randomized control trial, I don't think this method was this advanced. Maybe it was not yet developed. I don't know. I just guess, because I will not understand why you spend this amount of money when we know that the results of Mendelian randomization studies actually carry over in lots of time to randomized control trial. So if you had done this and found this, you would have been a bit hesitant about conducting this huge study and wasting this amount. It's not really a waste, because even if you have not found, it's still a good thing. Others will know that there is nothing there. But yeah. So that is the power of Mendelian randomization studies, and it brings us to the end of our presentation. So thank you for following to the end. And yeah, if you have any questions, you can ask now, please. Any questions? Il y a une question? Yes, monsieur. You can unmute your mic. We can't hear you. Please just unmute your microphone. Yes, please switch your microphone on, please.
Ok. Merci beaucoup pour la présentation. Elle est très enrichissante. J'ai plusieurs questions à plusieurs niveaux. Déjà, dès le départ, sur l'étude transversale. Lorsqu'on était encore à l'étude transversale, vous avez pris un exemple assez flagrant. Vous ne pouvez pas déterminer les facteurs associés et à la fin, vous donnez des conclusions sur les facteurs de protection et puis les facteurs de risque, alors que votre objectif était de déterminer une association. J'aimerais savoir comment est-ce qu'on formule les conclusions sur le plan du langage statistique qui soit acceptable. Ça,
oui, super. On peut parler d'association, merci beaucoup. On peut parler d'association positive et association négative. On peut dire qu'on a une association positive, c'est-à-dire que la tendance va dans le sens de dire, va dans le sens que lorsque X augmente, ça c'est positif, X augmente, Y augmente. Ça c'est une tendance positive, une corrélation positive, une association positive. Une association négative, c'est lorsque X augmente, Y baisse. Donc ça, c'est une association négative. Là, on aura les odds ratios inférieurs à 1.
Donc, oui, ça c'est très bien. Merci déjà. Maintenant, si là, lorsqu'on avance un peu, bon, je veux prendre un exemple assez courant. Par exemple,
excusez-moi, je voulais juste aussi faire une autre précision. Si vous êtes dans l'optique de déterminer des facteurs de risque potentiels avec une étude transversale, on sait que les études transversales ne sont pas les meilleures pour déterminer les facteurs de risque. Mais vous allez voir que pour certaines variables, on peut quand même se prononcer sans avoir peur de certaines choses. Par exemple, le sexe, comme l'âge. Il y a certains problèmes. Par exemple, les études transversales peuvent être exposées à la causalité renversée. C'est-à-dire qu'on ne sait pas, ça, si on veut parler de causalité, on ne sait pas si c'est X qui cause Y ou c'est Y qui cause X. Mais pour certaines choses, on sait très bien que rien ne peut affecter l'âge. Et donc, pour certaines variables, on peut parler de facteurs de risque sans avoir trop tremblé, comme on dit au quartier.
Allô? Bonjour.
Voilà, donc c'est un peu une précision que je voulais apporter. Donc, vous pouvez vouloir faire une étude. Je ne suis pas en train de dire qu'on ne peut pas faire des études pour viser la causalité avec les études transversales. On peut le faire, mais on doit le dire dès le début. Et tout le monde sait que les études transversales ne sont pas les meilleures. Mais si vous le faites, il faut le dire dès le début. Et progressivement, quand vous faites des discussions, je pense que ce serait mieux de souligner que vous avez pris en considération certaines lacunes du type d'études et que voilà un peu ce que vous pensez que la lacune là pourra avoir comme effet. Et voilà, je pense que voilà, c'est juste ça que je voulais ajouter.
Oui, en passant, la question suivante était de déterminer quelles sont les limites de ce type d'études transversales. C'était ma question suivante. Si on peut directement y enchaîner.
Ok, justement, c'est lié. Je pense que les limites, pour parler de limites, il faut déjà définir la question de recherche. Parce que si on veut déterminer la prévalence ou alors, oui, la quantité d'exposition d'une population, la quantité d'exposition à un certain facteur, vous allez voir que je ne vais pas... C'est l'étude la plus appropriée. À ce niveau-là, ça va dépendre de ce que l'examinateur ou l'investigateur aura rédigé comme protocole. Donc là, on va parler de lacunes qui seront spécifiques à ce que le chercheur a établi, a planifié. Maintenant, si c'est des lacunes dans la détermination des modèles de prédiction, il y en a. Si c'est les prédictions diagnostiques, je me dis qu'il y en aura un peu moins. Mais pour des prédictions pronostiques, faire une étude transversale, c'est possible. Mais je me dis que l'idéal aurait été peut-être une étude prospective pour faire une prédiction pronostique. Donc, parce que l'étude transversale est statique. Donc, on peut pas, quand on veut faire les prédictions pour le futur avec une étude transversale, on doit quand même être un peu prudent. Parce qu'on parle souvent pour faire les pronostics dans le futur, on fait souvent les études, les analyses de suivi. Et généralement, les études qui font des analyses de suivi sont des études prospectives, des études longitudinales. Maintenant, pour déterminer la causalité, pour établir un lien de cause à effet, il y a beaucoup de lacunes, il y a beaucoup de limites. Il y a d'abord le fait que pour certains facteurs d'exposition, on a ce problème de causalité renversée. C'est-à-dire qu'on ne sait pas qui a causé qui. Ça a commencé. Comment est-ce que ça a commencé? Est-ce que c'était le facteur d'exposition qui était là d'abord? Est-ce que c'était qui était là en premier? Il y a aussi les facteurs de confusion qui sont tellement nombreux ici, qui peuvent être tellement nombreux et certains sont même insoupçonnables. Et dans les études transversales, il faut vraiment que l'étude transversale soit extrêmement grande pour produire le genre de puissance qui va nous permettre d'intégrer autant de facteurs de confusion dans le modèle de régression. Sinon, on aura un problème. Donc, voilà quelques soucis qu'on peut avoir avec les études transversales en fonction des objectifs du chercheur.
J'ai très bien noté, merci beaucoup. Maintenant, c'est là, lorsqu'on se retrouve dans les études de causalité, s'il vous plaît, quel est le langage statistique qui convient le mieux? Comme tout à l'heure, dans les études transversales, nous disons il y a une dépendance positive, il y a une association positive ou négative. Dans ces études de causalité, quel langage statistique utiliser? Lorsqu'on a fait, par exemple, lorsqu'on a procédé, par exemple, à une étude de un essai clinique, pas un essai, oui, un essai contrôlé randomisé.
Oui, le truc, c'est que quand on fait déjà un essai contrôlé randomisé, automatiquement, on n'a même pas trop ce problème. Parce qu'on sait que ce sont les études qui sont les meilleures pour déterminer la causalité. Donc, quand vous utilisez le terme traitement, le terme exposition, même si vous utilisez un terme vague, tout le monde va comprendre qu'il s'agit en fait d'une cause. Donc là, c'est un peu, c'est clair. Je pense que de ce que j'ai pu voir jusqu'ici, la littérature est très flexible. Et le plus important, c'est qu'on comprenne exactement de quoi vous parlez. Et c'est pour ça qu'il faut prendre un terme et garder le terme là jusqu'à la fin pour faciliter la lecture. Si vous êtes en train de chercher un facteur protecteur, vous faites votre étude pour déterminer la force d'association entre ce facteur protecteur potentiel et votre issue, votre outcome. Moi, je pense que l'idéal, c'est de garder le terme facteur protecteur jusqu'à la fin et vous ne mélangez pas ça avec les autres pour ne pas embrouiller les lecteurs. Voilà ce que je pourrais dire. Mais sinon, je pense que dès que le principe est acquis, ça pourrait aller dans tous les sens. Du moment où on comprend de quoi vous parlez, je pense qu'il n'y a pas de souci. Et que vous arrivez clairement à vous exprimer, même si vous avez utilisé un autre terme et que vous avez clairement dit ce que vous cherchez. Je crois qu'il n'y a pas de problème.
OK. Sans monopoliser un peu la parole, je vous en prie. S'il vous
Il n'y a
plaît,
pas de souci.
lorsque, faites-moi une précision dans l'interprétation de... Lorsque nous sommes, par exemple, dans une étude d'association, je prends par exemple le cas du dernier cours. On disait ceci, lorsque nous faisons une étude, par exemple, transversale, la meilleure, c'est une étude d'association où on voudrait déterminer les associations entre les différentes variables. Maintenant, c'est là, on va dans l'interprétation de ces variables, on est souvent amené à calculer les facteurs, c'est-à-dire le odd ratio avec le odd ratio avec le risque relatif. Je me pose une question. Nous sommes souvent en erreur de le faire. Ça, c'est d'un. Et puis de deux, quelle interprétation tient le mieux si c'est bien pensé? Et puis, la notion de l'intervalle de confiance, je ne comprends pas comment est-ce qu'on interprète l'intervalle de confiance par rapport au odd ratio, ainsi de suite. S'il vous plaît.
OK. Déjà, si vous faites une étude transversale, vous n'allez pas avoir à calculer le risque relatif. Parce que les risques relatifs ne s'utilisent pas dans les études transversales vu qu'il n'y a pas eu de notion de temps. Donc, les risques relatifs, généralement, on parle souvent de ratio de prévalence, un peu comme ça. C'est qu'on va calculer ce l'autre ratio. C'est beaucoup plus approprié pour les études transversales et les études 4 témoins. Mais on utilise aussi les odds ratios dans les études, dans les essais cliniques. On utilise les odds ratios partout parce que c'est facile dans la computerization. Bon, l'ordinateur calcule plus rapidement avec les odds ratios. Bon, voilà. Donc déjà, on n'utilise pas forcément les risques relatifs dans les études transversales. Maintenant, vous parlez d'intervalle de confiance. Un truc que je n'ai pas mentionné, je ne sais pas si c'était une mauvaise chose, je n'ai pas mentionné, c'est que quand on soit en train de faire les prédictions, la causalité, les estimations, on va toujours essayer de déterminer le niveau d'incertitude. Parce qu'il n'y a pas d'études, je crois qu'il n'y a pas d'études qu'on va faire sans un certain niveau d'incertitude. On a vu ça dans notre Basic Health Research 1, là où on parlait de l'erreur en général. On disait qu'il y a toujours l'erreur. On n'est pas toujours certain parce qu'il y a les erreurs de mesure et on ne voit jamais toute la population. On est toujours en train de prendre une proportion de la population pour faire des conclusions qui vont s'appliquer sur toute une population cible. Et donc, il y a des erreurs. Et comme il y a des erreurs, il faut qu'on quantifie. Il faut qu'on quantifie le niveau d'incertitude. Bon, quand on quantifie le niveau d'incertitude, on prend toujours en considération plutôt les erreurs, je veux dire, erreurs d'échantillonnage, donc de taille d'échantillon, désolé. Donc, on aura l'intervalle de confiance qui est un intervalle qui va contenir la vraie valeur dans une certaine proportion de fois. Par exemple, l'intervalle de confiance à 95%, c'est un intervalle qui pourra contenir, c'est-à-dire que pour une étude, l'intervalle de confiance va vous donner une borne. Et dans 95% des cas, c'est-à-dire si vous reprenez l'étude là 100 fois, l'intervalle de confiance de toutes les études là va contenir la vraie valeur dans 85 études sur les 100. Ça veut dire que quoi? Quand vous avez votre intervalle de confiance à 95%, vous pouvez quand même dire avec un certain degré de confiance que la vraie valeur se retrouve dans l'intervalle là. Et vous espérez que votre étude n'a pas loupé la vraie valeur. C'est tout ce qu'on peut faire. On peut juste espérer que notre étude fait partie des études qui contiennent la vraie valeur dans l'intervalle de confiance donné. Donc, quand j'ai dit ici, dans la dernière, in the last part, quand je mets ici là, On aura beaucoup d'autres sessions là où on va parler de l'intervalle de confiance, des associations, des odds ratios, des trucs comme ça. Comme je disais, je pense que... Et là, on va devoir utiliser des datasets. On en a pas mal ici à Fishbone. Donc, quand on voit ici, là, il parle de risque relatif. Et le concept de l'intervalle de confiance s'applique pour tout. On peut avoir un intervalle de confiance pour tout. Parce que tous les paramètres qu'on estime, dont on fait les estimations en épidémiologie, sont assujettis à des sources d'erreur. Et donc, ce qu'on a, qu'on appelle le point estimate, est juste la valeur qui est bonne pour notre échantillon. On a besoin de savoir ce que d'autres échantillons auraient donné, ou alors quelle est la marge d'erreur qui accompagne une certaine estimation. Donc ici, ce qu'ils ont trouvé, et je vous assure, ici, là, ils ont inclus 35 000 hommes. Non, je veux dire, oui, je crois 35 000 hommes. Et ils ont eu ce niveau de précision aussi. Même avec 35 000 hommes, ils avaient besoin de déterminer, de quantifier l'incertitude de la force d'association. Donc, eux, ils ont trouvé 1,04, mais ça aurait pu être n'importe où la vraie valeur, entre 0,91 et 1,19. Donc, voilà un peu ce que c'est que l'intervalle de confiance et pourquoi c'est nécessaire. C'est pour nous donner une idée de l'incertitude qu'on a vis-à-vis de la valeur qu'on a retrouvée dans notre échantillon, dans notre étude. Ça va?
Merci beaucoup pour ces explications. Merci infiniment.
De rien, de rien. Est-ce qu'il y a d'autres questions? Are there any other questions? If there are no other questions, then we'll just say that that was it. Thank you for coming around and see you next Saturday. Bye-bye.